Hello and welcome to this talk on a new approach for finding low-weight polynomial multiples. The low-weight polynomial multiple problem is defined as follows. Given a polynomial p over f2 of degree d and the bound n greater than d, the goal is to find a multiple of p of degree at most this bound n and with the least possible weight. The weight of a polynomial over f2 is simply the number of its non-zero coefficients. The low-weight polynomial multiple problem finds application in cryptology in different contexts. The first and important one is correlation attacks against stream ciphers. It also finds application in finite field arithmetics. And finally, it's used to ensure the security of the public key crypto system by Phineas and Vodney. The algorithms for solving the low-weight polynomial multiple problem operate in two steps. The first step estimates the minimal weight omega, and the second step computes the multiples with that estimated weight. To estimate the minimal weight, one solves for omega the following inequality. Actually, the minimal weight is the smallest omega such that this inequality holds. Once this omega or this weight is estimated, then one looks for multiples with that estimated weight, using a variety of techniques that can be classified into memory-efficient techniques or time-memory trade-off techniques. And among these techniques, we find exhaustive search, discrete log-based methods, syndrome decoding, lattices, or the birthday paradox. We view the low-weight polynomial multiple problem as an instance of the celebrated subset sum problem. And this allows us to use the recent advances in the subset sum problem to devise new memory-efficient algorithms for the low-weight polynomial multiple problem, using more precisely the representation technique. Then we tune our solution into time-memory trade-off algorithms. The rest of the talk is organized as follows. We first present the group subset sum problem along with the representation technique. Then we present our approach to solve the low-weight polynomial multiple problem using the recent advances in the group subset sum, more precisely the representation technique. And finally, we present our time-memory trade-off algorithms. The group subset sum problem. The group subset sum problem is defined as follows. Given elements A1, An, and a target T from a group G denoted additively, and a weight omega, the goal is to find a subset of the AIs that sum up to the target T, such that the weight of the vector of the coefficients of this sum is equal to omega. Let now Z be a solution to the group subset sum problem. The representation technique consists in splitting the solution Z into a pair xy, which is a collision of two random functions f0 and f1 to be defined properly. So f0 and f1 are random functions from some set T to itself. The idea of the algorithm consists then in looking for collisions of f0 and f1 that satisfy the subset instance, which means that satisfy this equation and this weight condition. Of course, the larger the number of useful collisions, the better, because this will decrease the cost of the algorithm. So the challenge is to design f0 and f1 and consequently the set T, which is the domain and range of the functions, of the random functions, to allow as many representations as possible of the solution Z. Let's see some examples. Let Z be a weight omega solution, which is a binary vector of length n. How can one split Z? Well, the first idea is due to Howgrave, Graham, and Zhu, and they split Z into a sum of two vectors of the same length and of weight half the target weight. So this is a termwise addition. That means that every coordinate zi is the sum of the coordinates xi and yi for all i's. So with this splitting, we get two possible decompositions of 1. So 1 splits in 0 plus 1 and 1 plus 0, and we get only one decomposition of 0. Later, Becca, Courant, and Jou increased the values, the possible values for the coordinates x, y, and yi by the value minus 1, which adds two further possible decompositions of 0, minus 1, 1, and 1, minus 1. Recently, Essa and Mai split the solution, or the vector z, into a sum of two integers, and they investigate the carry propagation to further increase the number of representations of z. Now back to our low-weight polynomial multiple problem. Let this polynomial be a weight omega solution to the low-weight polynomial multiple problem. This means that this is a multiple of p, then we have this congruence. Now, if we denote by ai the residues x to the I mod p, then this congruence is equivalent to this equation. Now it's easy to see that z, the vector z, with the coordinates z1 up to zn, is a weight omega minus 1 solution to the following instance of the group subset sum problem. The group G is simply the additive group of the field f2 to the d. Actually, the residues x to the I mod p belong to this group, this additive group. The AIs are simply the residues x to the I mod p for I from 1 to n, and the target t is the first residue, which is equal to 1. The representation technique for the low-weight polynomial multiple problem. Let z be a binary vector of length n, and let x and y be vectors from the set T of vectors of length n. So T is the set of vectors of length n, binary vectors of length n, and of weight phi. Now, since we are operating over f2, then the natural way to split the vector z is to split it into a sum over f2 of two vectors from this set. So here, this sum over f2 is simply the termwise sum of the coordinates over f2, of course. Now, if the weight of z is equal to omega minus 1, then using standard probability laws, we have this equality satisfied, that is omega minus 1 equals to 2 phi 1 times 1 minus phi over n. Phi is simply the weight of the vectors x and y. And if we solve this equation for phi, then we can express phi as a function of omega and of n. Now it's time to define the random functions f0 and f1. So for this, we need a map tau from f2 to the d to the set T that we have defined here. Why do we need this map? Well, remember that the AIs here are the residues x to the I mod p, and therefore any sum of these residues is in f2 to the d. And since f0 and f1 are functions from T to itself, then we need something that brings us from f2 to the d to the set T. And this is ensured by the map tau. So now f0 of x is an element of T x is an element of T, is simply, so f0 of x is simply tau applied to this sum. So this sum is, the coefficients of this sum is simply the input vector. And f1 of x is tau applied to this sum, the same sum increased by the term a0, the first residue. Now let x and y be a collision returned by f0, or a collision of f0 and f1. So y is a collision of f0 and f1. That means that f0 of x equals f1 of y. So this means that tau of this quantity is equal to tau of this quantity. Now, since tau is injective, so here we need the injectivity of the map tau, then if we have the images that match, then this means that the pre-images match as well. Okay, and from this equality, it's easy to derive this multiple of p. So this is a multiple of p with a non-zero constant term and with degree at most n. Now, a memory-efficient algorithm for the low-weight polynomial multiple problem is straightforward. Given an instance of the problem, the idea consists in repeatedly looking for collisions of f0 and f1 that satisfy this weight condition. So once coming across a collision that satisfies this weight condition, we return M, which is built as follows from the found collision. We call a collision of f0 and f1 that satisfies this weight condition a useful collision. So with this, the cost of this algorithm is simply the time needed to find a useful collision times the cost of a collision. To estimate the fraction of useful collisions, we need to study the probability law of this random variable, meaning the weight of x plus y, where x and y are drawn uniformly at random from the set T. Remember that a useful collision is a collision that satisfies this weight condition. So therefore, our previous algorithm will be bifurcated into two algorithms, algorithm 1 and 2, and algorithm 2. Algorithm 1 assumes and puts in place a Bernoulli distribution on the vectors x and y, and therefore this random variable follows a binomial law, and this means that we get here a large probability p, but we get also a computation overhead due to putting in place the Bernoulli distribution on the vectors x and y. Algorithm 2 does not assume anything on x and y, and when studying the probability mass function of this random variable, then we get something similar to the hypergeometric distribution, and as a result we get a slightly smaller probability p, so slightly smaller than that computed here, but there is no increased computation overhead. We compare in this figure our algorithms with the memory efficient techniques for solving the low weight polynomial multiple problem. The x-axis denotes the relative weight, and the y-axis denotes the relative time exponent. So we can see that both our algorithms, so algorithm 1 and algorithm 2, both our algorithms outperform for almost the entire range of omega over n. Remember that the cost of our memory efficient algorithms is as follows. So it's a product of the product of the time needed to find a useful collision and the cost of a collision. Fortunately, our memory efficient algorithms allow for a time memory trade-off thanks to the parallel collision search technique, which reduces the time cost to this quantity, so this term reduces by a square root at the expense of this increase in memory. In this figure, we compare the time and memory costs of the state-of-the-art and our trade-off algorithms. So here we can see that our trade-off algorithms outperform in memory, and in general we can say that our trade-off algorithms achieve a nice time memory trade-off compared to the state-of-the-art. So to sum up, we used a new approach to solve the low-weight polynomial multiple problem by viewing it as an instance of the group subset sum. And this allows us to devise memory-efficient algorithms that improve the state-of-the-art using the representation technique. Our memory-efficient algorithms accept also time-memory trade-off using the parallel collision search technique. And finally, the long version of the paper is available on ePrint. And that's it. Thank you very much for your attention.